So you've been working with series and parallel capacitors, series and parallel resistors, and taking fairly complex circuits, reducing them down to one equivalent device, either a capacitor or a resistor, and then working backwards and filling in all your unknowns as you go. And you're thinking to yourself, wow, this is a powerful technique. I can look at really complicated circuits and figure out a lot about what's going on. So here's a circuit, and we can do that with this circuit, right? The two resistors on the left, R1 and R4, are in series, and the two on the right, R2 and R3, are in series. We can combine those into equivalent resistors, and then those two are in parallel with each other. So this is another circuit that we could solve. But let's take a look at this circuit. Did you see what I did? I added a fifth resistor connecting the two sides. See if you can reduce this down to a simpler circuit using your rules for series and parallel resistors. Did you try? There are no two resistors here that are in series, and there are no two resistors here that are in parallel. There's no way to simplify this circuit anymore using our rules for series and parallel resistors. What do? We need another tool. And I always say, any excuse to get another tool, right? In this case, the tool we need is Kirchhoff's rules. So today we're going to learn about Kirchhoff's rules and how we can apply those to solving complex circuits that we can't simplify anymore using our rules for series and parallel resistors and capacitors. Here's another circuit that cannot be reduced anymore using our rules for series and parallel devices. It's as simple as we're going to make it. We're going to solve it with Kirchhoff's rules. So if we were given the resistor values for R1, R2, and R3, and the battery voltages V1 and V2, and we wanted to find the current in every branch of the circuit, so the current through resistor 1, the current through resistor 2, and the current through resistor 3, we would do that with Kirchhoff's rules. And these rules aren't too difficult to apply, but there's a lot of little details. So if you pay attention to the details and the signs and the directions, it usually works out nicely in the end. Especially as your first attempt doing these problems, write out every step, don't skip, think about each direction and each sign, and make sure you understand why it is the way it is. The first thing we're going to do is define the direction of the current in each branch of the circuit. This circuit has 3 branches. There's a junction down here, and current can come this direction to the left. And once it takes that path, it has to go all the way around to the top. There are no forks in the road. There are no other branches. It can take a different path. Once it's on this part here where battery V1 is, it has to continue all the way through to the other side. The same is true with the middle branch. Once the current decides to take that path, it has to go all the way to the top. And the same is true of the last path. Once it's on that path, it has to go all the way around until it finds another branch, another fork in the road where it can change direction. So there are 3 branches in this circuit, and I'm going to call the currents I1, I2, and I3. And we need to pick a direction. What direction is the current going through branch 1? Is it going this way? Or is it going the other way? We don't know. So we're just going to guess. The nice thing about this is all the signs change in the end if we guessed incorrectly. So we don't have to guess correctly right at the beginning. If we get it wrong, we just get a minus sign in our answer for the current. Most of the time, not always, but most of the time, current is going in the direction of our battery. The battery pushes the current out the high voltage terminal, and it comes back in the low voltage terminal of the battery. So typically in our circuits, that's the direction of the current. So we can pick that as our direction, but it doesn't matter. We can pick any direction we want. So in this case, I'm just going to go with that convention. I'm going to say I1, the current through resistor 1, is going in that direction, the direction the battery would push it. And I'll do the same thing with the middle branch here, and I'll go with the direction the battery would push it. And now I have to pick a direction for the current through I3. If I1 is going the direction I picked it, and I2 is going the direction I picked it, then what must be happening to I3? It must be going that way. All that current is coming into the junction at the top here, this junction. All that current, I1, is coming in from one side, I2 is coming in from another side. Well, where's it going? It must be going out towards R3. But just to show you that we can pick any direction, I'm going to pick this as my direction. So I know that at least one of these has to be wrong, because all the current can't be flowing into the top. Think about water. If you had 3 pipes and all the pipes had water flowing in one direction, where the 3 pipes came together, there'd be a problem there, right? Where's that water going? It's the same with electrical current. That current has to go somewhere. So I know at least one of these is wrong, and this way we'll get to see what happens at the end when we get one of our directions wrong. So number 1, define a direction of the current in every branch, and it doesn't matter if you know the direction or not, we're just guessing here. The next thing we're going to do is apply the junction rule. The junction rule tells us that the total charge can't disappear or appear, right? Those charge that's moving through a wire, those are physical particles, electrons with mass. They don't just disappear. And the current that flows into a junction has to equal the current that flows out of a junction. So we'll call this junction A. All the current flowing in has to equal all the current flowing out. And so in this case, I have all 3 flowing in and nothing flowing out. So my equation would be I1 plus I2 plus I3 is equal to 0. We could have picked the other junction, junction B at the bottom. What would we get if we picked that junction? Let's see. We have to follow these tails around. I1 is coming out of B, and it's going up this side and around and into A. I2 is flowing up the middle, and I3 is flowing this way and up and around this side. So if we look at B, we have nothing flowing in, and we have all 3 flowing out. We get the exact same equation. So there's no new information here. Even though this circuit has 2 junctions, they are a pair. Whatever equation we get for one junction is the same exact equation we get for the other junction. So this gives us one equation. We have 3 unknowns, so we need at least 2 more equations, don't we? Let's take a look at our next step. Now we're going to mark each device in our circuit, each battery, each resistor, with a plus and a minus to indicate which side is at higher electric potential. And we have a couple of rules here. For a battery, we're told which side is at higher potential. The long line is the high potential side, and the short line is the low potential side. So I would mark it like that. For a resistor, it depends on the current. We know current is the flow of positive charges through a circuit if positive charge is moved. And positive charges would move in the direction of the electric field. And the electric field always points from high potential to low potential. So if the current in this resistor is going to the right, if positive charges are moving to the right through my resistor, the electric field must be pointing that way, and the left side must be at higher potential than the right side. So I would put a plus over here and a minus over there, because I know I flows from high to low potential. This is the high potential side, this is the low potential side. High, low. So my batteries are easy. I just look for the long terminal, the long line. Now the resistors. R1, my current is flowing up. So the bottom has to be at higher potential than the top. R2, my current is flowing up. So the bottom has to be at higher potential than the top, or the current wouldn't be flowing that way. And I3, it's going up. So the bottom must be at higher potential than the top. Now I'm ready to apply the loop rule. The loop rule says that the sum of all the potential differences as you go around a loop in a circuit has to add to 0. And it's like my hiking trail analogy. If you start out at a certain place and you go for a hike and you go up a hill and down a hill and up a hill and down a hill, and you end up at the exact place you started, you have to be at the same elevation again. And that's the loop rule. If you go around a loop, if you start in this corner and you go around this loop and come back to this corner, whatever the potential was when you started, that has to be the potential where you end up again, because you're back in the same place. So all the potential rises and drops as you go through that loop have to sum to 0. Now, there are 3 loops here. There's the loop on the left. There's the loop on the right. And there's the perimeter on the outside. So we have 3 loops to choose from. But we can't choose all 3 of them. If we used all 3 loops for our 3 equations, and we did not use the junction, and we were trying to solve for I1, I2, and I3, at the end, we would just get 1 is equal to 1. We wouldn't get any useful information out of that. And the reason is that one of those 3 loops contains no new information. Once we do this loop and this loop, or any 2 loops, I just picked those 2, we've covered everything in these circuits. There's no new information from the last loop. What I like to do is always start in the same place. And as I make my loops, I keep incorporating new devices. So I'll start here, and I'll call this loop number 1. I'll use green. And then I'll start there again. And this time I'll incorporate R3, and I'll call that loop 2. Because you want your loops, every loop has to have at least something new in it and at least something that connects it to something you've done earlier, to a previous loop. So if you always start in the same location, and then you go around and you make your first loop, and then when you make your second loop, you incorporate something new and come back, then you're guaranteeing yourself that you've got something in common and something new in each of your loops. So let's do these two loops. Loop 1 is that green path, and I'm going to start in the lower left corner and go around the loop in that direction, clockwise. I'm going this way, right? First thing I do is I hit the low voltage terminal of battery 1, and I go in the low voltage terminal, and I come out the high voltage terminal, so I've gone up by V1. I'm now at a higher potential than I was. I've risen by the voltage difference on that battery, V1. That's a rise of V1. The next thing that happens is I go in to a resistor, and I come out the other side. This is why we draw the little plus and minus signs. For the battery, I know I went in the low voltage side, and I came out the high voltage side. So I had a rise of V1. For the resistor, I see I'm going in the high voltage side, and I'm coming out the low voltage side. So I'm dropping by the voltage across resistor R1. And what's the voltage across a resistor? I times R. So I'm not going to write it this way. I'm going to write it as I1 R1. So I've dropped by the voltage across resistor R1, and the voltage on a resistor is I times R, the current through R1 times R1. Let's see, what's next? I continue around this circuit, and now I'm going to come down this side over here, and I'm going into resistor R2. I'm going into the low voltage side, the low potential side of resistor R2, and I'm coming out the high potential side. So this is a rise in voltage, a rise in electrical potential, even though I'm going through a resistor. Over here, I went through a resistor, and I had a drop in electric potential. And here I'm going through a resistor, and I'm having a rise in electrical potential. Because in one case, I went in the same direction as the current, and in the other case, I'm going opposite the direction of the current. So I'm rising by the voltage across resistor R2, which is its current, I2, times its resistance. Now I am coming up on battery V2. I'm going in the high side, and I'm coming out the low side, so I'm dropping by that voltage. Over here, I went through a battery, and it was a rise in voltage because I went in the low side and came out the high side. But over here, it's a drop in voltage because I went in the high side and I'm coming out the low side. So picking a direction and staying with that all the way around your loop is very important. Let's see where we are in our circuit. After I come out of battery V2, I make my way back to where I started. I don't encounter any more devices. So the sum of these four potential differences has to be 0. That's my first loop equation. Now I'll do my other loop. The red one. First thing I do, I start in the lower left corner. I'm going clockwise around my circuit. I encounter battery 1. I go in the low potential side. I come out the high potential side. So I have gone up by V1. Then I encounter resistor R1. I'm going in the high potential side, coming out the low, so I am dropping by I1 R1. Now I come this way, and I encounter resistor R3. I'm going in the low potential side, coming out the high potential side. So that's a rise. And then I go back to the battery without encountering any more devices. So here are two equations, loop 1 and loop 2, and a junction. It gives me equation 3. So I have 3 equations. I can solve for 3 unknowns. In this case, it's I1, I2, and I3. So let's use these values for R1, R2, R3, and my 2 batteries. And if I plug in these values and do a lot of algebra, I end up with I3 is negative 171 amps. So that tells me that I picked the wrong direction for I3. And I knew that when I was picking it, right? I kind of knew that this was not going to be the right direction, but I picked it anyway. So now my equation just confirmed that. By getting a negative value for my current, I know it actually goes in the opposite direction. But I can't change it yet. I've just solved for I3. I did a whole bunch of algebra. I solved for I3. Now I have to plug I3 back into one of my other equations to solve for I2. And what do? I don't change the sign, because I came up with all of these equations based on I3 going in the direction I chose, which is the wrong direction, it turns out. But all those equations are based on that. So now, when I go back and plug in I3 into my next equation to solve for I2, I plug in negative 171. I keep that negative sign and keep using that until I'm all done finding all my currents. Next thing I get when I do this, I get I2 is negative 0.283 amps. And then to solve for I1, I would use my junction rule. Remember, I plug in my negative 171 for I3 and my negative 0.283 for I2. And now I can solve for I1, and I get a positive 171.283 amps. So that tells me the actual flow. The actual flow in this circuit was current going up this way, down here, and down there. And the reason we get this flow is that this circuit is designed to recharge a rechargeable battery. You would never want to push current backwards through a battery that's not rechargeable. But that's how you recharge a battery. A chemical reaction is taking place in that battery and that forces current to flow through the circuit. And when you put the current backwards through the battery, it reverses the chemical reaction and you can recharge a rechargeable battery. But as I said, you never want to do that with a battery that's not rechargeable.